So I actually I'm going to tell you guys a little bit of a story. I made a bunch of videos with me just kind of doing the test and talking to you as I was walking through the test. And then they were kind of long and I said, yeah, maybe this wouldn't. And then I looked at them and as you can see, I'm kind of using two cameras, one to do what I'm writing and one to show me. And the one that was showing us writing was not positioned properly most of the time. And so I said, okay, you know what? I'm not even going to worry about it. They'll be fine without it. Then I graded all the tests and I said, you know what? I should do this because I think it would be valuable at this point for you guys to um, hear what I'm thinking as I'm going through the solution of a test. And so what I'm going to try to do is make this super fast. So I'm going to try to go through here and um, just make it just stop and go back if you need to stop and go back. So I'm going to pull my copy of the test out. All right, multiple choice questions. Antenna top of the Empire State Building, 443 meters above the ground. How far does the charge is on top? How far does the electric field extend? The electric field associated with the charge fills all space. So that's B. Second one is take that charge, that's the top of the Empire State Building. Take that and let's say we've got this charge, which is this height. We'll just call it D at the moment. Above this charge here, and this is a mass M, a charge. Let's see, is this the one that has the charge? Yes. This is our steel marble that has a mass M, a charge Q, and up here we know this D. And the question is, what is Q in order to get this to leave the ground? So I'm going to go ahead and write in my X, Y coordinate system and what are the forces that I have operating on this. So now I'm just going to take this steel marble and put it over here. And I've got steel marble. I know it's got mg down. And I know it has k q1 q2 over r. Since I did d, I'm going to go ahead and do d squared. This will be the force up. And you do need to be certain to think about this because we're kind of playing a little bit casual with all the signs and all that kind of stuff. We aren't really worried about putting the vector signs because everything is in one dimension. So when it's in one dimension, it doesn't matter that much. So you do need to be aware that in order for this to be an upwards force, remember this is F21 is this distance here, 1, 2. And so that's going down, so this would need to be a minus sign in order for this to be an attractive force, which means that whatever we do for, since Q2 down here is positive, Q1 needs to be negative, and the question is, and what are our choices? We're given 100 coulombs, 1 coulomb, or 0.001 coulomb. Okay, as soon as I see this, I say, you know what? I don't really need to calculate this accurately. I just need to see what's closest to one of these things. And so I'm going to go ahead and cheat and do a few things that will make my life easier. So one of those things, let's see, so we need K, Q1, Q2 over D squared. So we have D is 443 meters. Excuse me, that was another thing that happened is that last night I was a little congested as I was making the video and hoping it would get better, and unfortunately today it's a little worse, so I apologize. So there'll be a couple coughs here and there. Okay, so I know D is 443. I know this Q is 2.1 times 10 to the minus 4 coulombs, and I know K is 9 times 10 to the ninth. And I know G, the acceleration of gravity, is 9.8 meters per second squared. And we do need to do this. Newton meters squared per coulomb squared. Okay, coulombs, this is meters, and we're looking for this in coulombs. Okay, so that's what I'm thinking about, and now I'm just going to look at this and just do this calculation. Well, what do I want to say? I want this upward force to be at least equal to, so this force, the electrostatic force, is going to be greater than or equal to mg in magnitude. All right, so what is our m? It's 1 kilogram. I didn't write that here. 1 kilogram. And so now we just need to know, when does this F up greater than F down? And that will mean it's leaving the ground. Okay, so I want to make sure this is here, so I'm going to go ahead and cheat a little again. So I just need to do my K, Q1, Q2. Well, K is 9 times 10 to the 9th. Oh, I'm sorry. Let's go ahead and solve this equation. We're going to go ahead and solve this equation. F is greater than or equal to mg. F is greater than or equal to mg. So that, and I know F is K, I don't know why I need to look that up. K Q1 Q2 over D squared is greater than or equal to mg, and I want to solve for Q1. So this is going to be equal, greater than or equal to mg D squared over K Q1. Excuse me, KQ2. Q2 is the one on the ground. All right, so what do we know? We know M equals 1 kilogram. We know G equals, and this is the first time I'm going to take advantage of the fact that I don't need to be super accurate, because I've got 2 orders of magnitude to work with, 4 orders altogether to work with, but 2 orders of magnitude are separating every answer, so I'm just going to call this 10 meters per second squared. And D, let's just go ahead and call it 500 meters. And K is 9 times 10 to the 9th Newton meter squared per coulomb squared. And Q2 is in coulombs. Let's just go ahead. What was it? 2.1? Yeah, let's just go ahead and call it 2. 2 times 10 to the minus 4 coulombs. So first, let's check the units. We have kilograms times meters per second squared. So we have kilogram meters per second squared times meter squared. So we have kilogram meters cubed. Where was I? Oh, per second squared. And what do we have in the denominator? We have Newton meters squared per coulomb squared times coulombs. So in our denominator, we have Newton meter squared per coulomb. So we're going to multiply then this when we solve this, and I realize I'm doing the same thing. That's probably not in the camera. When we solve this, I just am going to verify that my equation looks good. So I'm just doing the unitary analysis. C Newton meters squared. And so the question is, what is a Newton meter squared? Well, that is a kilogram meters. Well, I'll excuse me. I'll do it this way first. Kilogram meters per second squared. But it's times meter squared. So what I have down here is a kilogram meters cubed per second squared. So I have kilogram meters cubed second squared. They all cancel with Newton meters squared. And the only thing I'm left with is C, which is coulomb. So I know my equation, or I'm confident my equation is right. And now all I have to do is do the numbers. And if we do this, we find this is 10 times 5 times 10 to the second squared over 9 times 10 to the 9th and 2 times 10 to the minus 4. All right. So now we just have to do this, and we just say, all right, this is 25 times 10 to the 4th, which is 2.5 times 10 to the 5th, but it's multiplied by 10, so that's 2.5 times 10 to the 6th. And what do we have in the bottom? We have 9 times 2, that's 18 times 10 to the 5th. What did I say, 18? Yes, 18 times 10 to the 5th, which is the same as 1.8 times 10 to the 6th, 1.8 times 10 to the 6th. And I look at this and I say, you know what, 2.5 divided by 1.8 Is that ratio equal to 100? My 10 to the 6th cancel out. So is that equal to 100? Is it equal to 100th? Is it equal to 0.001? No, it's really close to 1. So I know that my answer is C1. All right, then the question is, here's this thing. Once this force moves this above the ground, so I'm now at this new location here. I'm now at a new spot that's slightly above the ground. Here's the question. Is the force between the top of the antenna and this charged ball, is it greater now? Is it the same, or is it smaller than it was when it lifted off the ground? Well, what happened? The distance here got smaller. When this lifted off the ground, this d is now d minus a little bit. Well, d minus a little bit, look at our Coulomb's law. If this is a little bit smaller, the force is a little bit bigger, which means as this lifts off the ground, the closer it gets, the greater that force will be. So this is going to speed up until it just crashes right into the top of the antenna, which is number B, or choice B, for number 3. All right. Let's go into the next page of multiple choice. Paper bag sits on a table. I'm just going to go ahead and save some paper doing like this, even though it's not really clear, or it's a little... Paper bag sits on a table. Next to it is an uncharged massless marble 3 centimeters away. So I know this distance. Well, the question is there a charge? What can we say about the charge in the bag? Well, what's the force? It's the same equation we use for every single problem here. K, Q1, Q2 over R squared. So there's some unknown Q here. I'll call it Q2. With this Q1 here is uncharged, which means it is 0. So if I have Q1 that is 0 and I put it in this equation, what's this equation going to equal? No matter what Q2 is, it's going to be 0. So there is not enough information to say, so that's choice number A for number 4. Uncharged metal plate extends to infinity in the x and y directions. A small metal ball holds an infinitely large but measurable charge Q and touches the metal plate, then is removed. What describes the situation after? All right, so this is, there's a little potential confusion in this one. So I'm actually going to remove the points for this from the total, but if you got it right, I will keep your points in the percentage. So if that makes any sense, I hope that kind of makes sense. So I'm not going to subtract 4 off of what points you got, but I will subtract 4 off the total, which means your percentage will be a little higher. The confusion is in this whole idea of you have an object here that has, we are told, an infinite but measurable charge. And so when you look at that, I could see that you would say, but wait, this is so much, I'm going to put this in contact with this plate, and this plate is going to accept way more charge than this thing could hold. And the way to think about it is the charge density here and the charge density here would have to be the same in order for the forces to be equal. And we know that when forces are equal, that charge will move in a conductor until the forces are equal. So we know that the trick is that because we call this an infinite charge, what we're saying is no matter how much of this goes to the plate, it's still going to have half of it left. That's a little, I can understand where that might create some confusion. So like I said, I'm taking this off. But the point is this. This is the important point from here, that when these come in contact, these will now share charge until the forces are equal on the charges between the two objects, which is related to the charge density on them. And what are my choices? Oh, and because this is a conductor, those charges cannot stay all next to one another if there's no charges out here. They're repelling one another. They're similar charges. They're going to repel until they are pushed back with just the same force that they're pushed this way. So they're going to spread evenly all throughout the plate, all through infinity. So the answer there is a charge of Q over 2 is spread all over the plate, which was answer D. All right. This one is kind of important also. We will be working on this later, but this is conceptually, this is how you should be thinking about this. This is number 6. Number 6 says we've got a plate with charge sigma on it. We are told, excuse me, that this plate with a plus sigma has a field of sigma over epsilon 0. We are also told it has, we're also told it fills all space, so we know sigma over epsilon 0 there as well. So this is our beginning situation. Then we put an identical plate over here. This identical plate is exactly the same, except it has a minus sigma charge and not a plus. So everything is going to be exactly alike, except these fields are going to be in the opposite direction. Now, look in there, and so it's going to be same magnitude, sigma over epsilon 0, but the direction is going to be opposite. So look at way over here. Here, I have a sigma over epsilon 0 going this way. Here, from this plate, I have a sigma over epsilon 0 going this way. So here, E equals 0. Over here, I have a sigma over epsilon 0 going this way. And from this plate, I have a sigma over epsilon 0 going this way. So the field is going to be equal to 0. But look right between them. Here, I have an a sigma over epsilon 0 in this direction and another sigma over epsilon 0 in this direction, which means electric fields add, principle of superposition. We've used that for almost every problem. So, which means that our total field in between is 2 sigma over epsilon 0. So the right choice there is field between the two plates is 2 sigma over epsilon 0, and the field outside is 0. Okay, number 7. Paper bag sits on an uncharged table. Nothing else is around. I'm going to draw my paper bag. Nothing else is around. A measurement shows there is an electric field. What can you say about charge in the bag? Can there be an electric field without a charge? Can there be charge without an electric field? No, they are different manifestations of the same thing. That's like, all right, you might quibble with my example here, but that's like my banana example, right? Can you have the taste of the banana without having the banana? Well, if you're making things in the lab that taste kind of like banana, you can simulate it, but like banana BB bats, but I think they stopped making those, but those were good. Really fake, though. Okay, so the answer is if I have any electric field here in any direction, I must have a charge in here, an excess charge in here. But can I say anything else about it? No, I can't. The only thing I can say is there's excess charge in the bag, which is choice B. Number 8, imagine this were true. A, B, C are all charged. So object A attracts object B. Object B attracts object C. Object A attracts object C. So I've got this kind of situation. These all, well, I'm drawing it like this, but we're going to say that this is all attract. So what do we know? We know opposite charges attract. So A is the opposite of B. B is the opposite of C. C is the opposite of A. So what needs to be true for that to happen? The only way that can happen is if there are more than 2 types of charges, if there are more than 2 opposites. And and what and the reason I brought this up is because I want you guys to be clear that the reason you know there are 2 types of charges, because when you do this experiment, you say this attracts this attracts this, then what happens between these 2? They repel. Okay, so it's the opposite thing that happens. So the opposite of B is A, the opposite of B is C, and A and C are the same, therefore there are only 2 types of charges. Okay, but for this problem I said what if they all attract one another? So that would mean there was more than 2 types of charge. Doesn't mean there's only 3, you'd have to do a lot more testing. This is not the way our universe works, but if we had seen this, that would have been how it worked. And there's no reason why there only had to be 2 types of charge. Okay. There are some really fancy theories that tie into the Big Bang and evolution of the universe and particle physics at high energies and all that explain why there's only a couple types of charge. But it didn't have to be that way. It just turns out that that's the universe we live in. All right, imagine this situation. An electron and a proton are always, I'm going to use this here because I don't have much to write for these multiple choice. Okay, an electron E minus, and a proton, P plus, are separated from each other by the Bohr radius, and that's just some distance here, which is A0. Okay, what must be true? All right, so here's what we're looking at. An electron and a proton. What are their charges? Their charges are opposite. Therefore, what are they going to do? They're going to attract one another. So, when they attract one another, they will, if they attract one another, they're going to do the same thing that steel marble at the ground outside the Empire State Building did. They're going to get, the attraction is going to get stronger and stronger as they get close. Therefore, if they attract one another, it means that there must be something holding them apart. Now, something is just some force. We don't know what it is. But on the other hand, if this electron was kind of whirling around in a circle, that would create a centripetal acceleration. So that would be, there would be a force there that would counteract the moving down. So I will accept for this one, I will accept A, B, or C. As a matter of fact, I did accept A, B, or C for that one. All right, final one. This is also important. I got 13 charges all around. I'm going to draw them like this, and I'm actually not going to draw all of them. But it doesn't matter how many they are, how big they are, what's going to happen at some point P. This is my point P. At some point P, they're going to add up. They're going to add up like vectors. This one is going to add up. Let's say that this is positive and this is negative, so this is going to add like that. And then this one over here. So I've got all these vectors that correspond to each of these individual fields at this point. But what's the sum going to be? It's just going to be one vector in some direction. How would you be, what's the minimum number of charges you would need in order to counteract this electric field that's due to some, that's in just one direction? One charge. I can pick the right kind of positive charge here and push this way an equal amount. I can pick the right kind of negative charge here and do this in equal amount. But I only need one because it sums to just one single vector. Okay, so that's a multiple choice. I'm going to stop and I will do the other ones individually and we'll see how we can do it.